All right. Hello to those of you who haven't been here for a while or are here for the first time. We're going to start just by reviewing some of the various properties of schemes, all the very, very many that we've talked about. Just basically list them by name, but if anybody wants to just have me briefly describe one of them, I'm open to that before we dive in. But we can basically sort them into three main categories, because some of them just depend on just the topological space that underlies your scheme. Some of them have more to do with the sheaf of rings, and so they become algebraic properties. And some of them are structural in that they force like everything about the scheme at the same time. So like if you know a scheme is affine, you know both what its topological space looks like and what its sheaf of rings is. But again, apologies to those of you sitting on the far end of the room. But the topological ones, so we talked about connected schemes, irreducible schemes, both having to do with breaking up your scheme into open sets of different kinds. Quasi-compact and quasi-separated. Quasi-separated I'll remind you of, just in case, because that one's a little foreign. That was just the intersection of quasi-compact open sets is quasi-compact. And then on the level of points, well, you can talk about closed points, self-explanatory, or generic points. And generic points are actually going to turn out to be important in what I'm going to tell you about today. Turns out these associated points I'm going to tell you about are generic points of certain things. Okay, and then we had the plethora of algebraic properties that, yeah, we had reduced, we had integral, we had both locally Noetherian and Noetherian, we had A-schemes, which was just schemes for which the structure sheaf over any open set was an A algebra, and all the restriction maps were A algebra maps. And then special types of those were locally finite type A schemes or finite type A schemes, depending on how many spec of A algebras you needed to cover your scheme. Normal and factorial, that was the subject of last week. Anton talked about this, and it was just a property of stocks. If all the stocks were UFDs, then it was factorial. If all the stocks were integrally closed integral domains, then we had normal schemes. And then the structural properties, well, we're quite familiar with affine schemes by now. That was a lot of what we talked about. Projective schemes, we spent a few weeks talking about. Quasi-projective ones, which were quasi-compact open subschemes of the projective schemes. And affine K-schemes I just threw in because they're the analog of affine varieties from classical algebraic geometry. So it was just spec of a K-algebra, but that K-algebra had to be reduced and finally generated. That was it. Okay, so I said to our newcomers way back in the day that, or at least at the beginning of this term, if you're coming into the seminar, it would be sufficient to know what a scheme is and how to work with schemes. Now I would say if you're comfortable with these adjectives, then you're probably all in a good place. Okay, anybody want me to just elaborate slightly on any of these, or is that all, we're all good? Okay, just wanted to remind us of these.
May I ask?
Yes, sir.
Can you quasi-projective variety? Because I meet this term all the time, but I don't remember what it is.
Quasi-projective scheme?
Quasi-projective scheme.
Yes. Okay, so you know what projective scheme is, right?
Yes, I do.
Okay, so any open subscheme of a projective scheme that is also quasi-compact.
Oh.
That's it. Cool. All right, so, well, I made another attempt at a pun because we are talking about associated points today. These things are, well, Vakil calls them points of a scheme that are supposed to control everything. They only work in the context of locally Noetherian schemes, and it's going to take us a while to even get there. I'm not going to get there today. That'll be the next speaker. Jala, sorry, that'll be your job the next time. But what these things do is, well, they have at least two reasonable purposes. One of them is to detect where in your scheme non-reduced behavior lives. So we saw that a scheme is reduced if and only if all of its stocks are reduced. So if we have a non-reduced scheme, then at least one of those stocks is non-reduced. And if you understand actually what happens in the stocks at all the associated points, you're actually going to be able to write down exactly at which points you have non-reduced stocks. The other one is going to be if you want to try and define rational functions. We've seen how this is done on an integral scheme to some extent, but this can be done for a locally Noetherian scheme if you know what these associated points are. And that's something we will also eventually see. But like all situations, we're going to start with the affine case, figure that out, and then deal with the general case afterwards. Okay, before I do any of that, though, I have to bring back a definition from the deep dark past. We talked about this last fall when we were talking about sheaves. So we can make this definition. Just for any ringed space. So if X is a ringed space, and you give me any global section of the sheaf, any function on X, we define the support of the element it's the following. So you look at all points in your scheme where the image of f in that stock is not zero. Okay, so in particular this applies to schemes. And one fact we did, also from that deep dark past, sup f is always closed. Just to give you a reminder of how that proof works, what you do is you show the complement of this thing is open. And so if you've got a point at which the image of f in that stock is 0, then basically by definition of stock, I can find you a neighborhood of the point on which f restricts to the 0 function. And then at every point in that neighborhood, I'm going to have a 0 stock, or 0 germ in the stock. And so that proves the complement is open, and so we're all good. So I want to also bring up something, this is new. We're going to talk about the support of a module element, because that's where all this action is going to be happening. So if I've got an A module, and you give me an element of the module, we'll define the support of any element of M to be going to be some subset of spec A, defined in an analogous way. So we're going to ask that this thing that I call MP should not be 0. Where now MP is the image of this element in the localized module. So we can localize a module at the prime ideal just like we can do with a ring. It's just all your numerators of your fractions are now elements of the module, but all the other definitions are the same. Okay, so it turns out this is also closed. But I can't give the proof in the same way as I did here because I don't really have any germ action happening. So how do we actually do this? So we prove, again, the complement is open.
Sorry, Nick, I just want to, so you've got little m's and big m's.
Yeah.
So I just want to make sure that I have them all right.
Right. I will maybe make a point of doing something, support of little m.
That has all little m's. The only
Yep.
big M is in the localized module, big M.
Right.
Okay, good. I'm glad I had that.
I may start to do this for my modules,
Okay.
and then we'll all be
Yeah.
good. Okay. So yeah, we want the complement of this to be open. So just take any prime ideal, not in the support of M. And I want to find a neighborhood of this, also disjoint from the support. Okay. So if you unwrap the definition of this, so we know MP has to be 0. And so by definition of localization, that means I can find you an element not in P such that if I multiply by this element, I get 0. With AM equals 0. Okay. Well, my neighborhood now, the good candidate neighborhood would be DA. So consider DA. So P is certainly in there, so it's a neighborhood of P. And if I've got any other prime ideal in DA, then this relation AM equals 0 witnesses that MQ is 0. So we're done. Okay, so we've got these closed things. And the associated points are going to be related to the supports of elements. So we first define associated points of a Noetherian ring A. Because it's all going to be Noetherian with this. Or more generally, of a finitely generated module, a module, M.
Yeah, not much happening.
Very good. Okay. So what are these things? What are these associates that I'm scheming with? Okay, so we're going to let M be one of these modules. Over Noetherian A. And I'm going to stop writing this now because all my rings are Noetherian for the rest of the day. Okay. The associated points of M are the generic points of the irreducible components of elements or of sets of the form sup M. Or I'm going to let M range over everything in the module. Okay, so the supports of all these elements, we know they're closed subsets of spec A, and spec A is Noetherian. So the nice thing about Noetherian schemes, or Noetherian topological spaces, is that any closed set can be written as a finite union of irreducible components. So each of those being irreducible has a unique generic point, whose closure is the component, And you just take those points, and those are the associated points, where you do this for every one of those elements of the module. Okay, so this is, there's sort of two ways of going at this, defining these things. So if a kill does both, we start with this, which is the geometric approach, and we just basically take some things as axioms about these points, and we deduce really useful consequences. Then we go back and make an algebraic definition and prove that it coincides directly with this version of associated point. So that's sort of probably going to take us 2 weeks after this, but by the end we'll have a good understanding of these. Okay.
Generic point is just something which closes to the whole thing?
Right. Yeah, the closure of one of these would be the entire irreducible component.
And these, I feel like you just said this, but they always exist?
Yes, any irreducible subset has a unique generic point. This was, I think, it was something I did, I think.
I missed
but
okay. Thanks.
Yeah, it's another one of these things, you do it for affine schemes first, where it's sort of almost evident. Yeah, and then you do it for the general schemes using some fancy argument. Okay. So we have the definition, but probably some examples are needed. So in the case of, and I'll get rid of this now. In the case of when your ring is an integral domain, life is simple. Turns out there's only one associated point ever. So we've made, like the definition I've made applies to any module over a Noetherian ring, but usually we'll be interested in the case where the module is the ring. And then we're just dealing with the affine case, spec A, what are its associated points. So most of what I'm going to do today is in that context. Okay, and I will no longer write over here. Okay, so suppose A is an integral domain. That it turns out the zero ideal is the only associated point for A. Which maybe we would expect, because when you're dealing with, say, the fraction field of an integral domain, you're just localizing A at 0. And if I'm going to talk about rational functions on some locally Noetherian thing, then I want to localize at associated points. So in this case, we're just going to recover A localized at 0 and recover like what we would think is the fraction field. Okay, so how do we do this? So this one just boils down to actually like exhaustively analyzing the supports of different elements. So support of 0 is the easy case. This is empty. Because I want to look at all the localizations of A in which 0 becomes non-zero in the localization. But that seems really silly. That's never going to happen. So we've got that. Okay, now if I've got a non-zero element of A, the claim is that the support of F is spec A. This is just something we run through with the definition. So you want to check that if I localize at any prime ideal, the image of F in that localization is never 0. So for P in spec A, check. We check that FP is not 0. But what would it mean for FP to be 0? Then I could find you some A that's not in P such that a times f equals 0. Well, now we're in an integral domain. So this implies a is 0 or f is 0, but f wasn't 0. And a is not in a prime ideal, and 0 always is. So this doesn't happen either, so we have our contradiction. And so sup f is spec A. Okay, and so since we're integral, since we're dealing with an integral domain, spec A is irreducible, so it's the irreducible component of sup f. And it's actually equal to the closure of the 0 ideal. So we recover 0 as the generic point of this thing, and therefore the only associated point. Okay. So at least with some rings, this apparently complicated definition is not so bad to work with. All right, so let's look at a little more exotic example. Now I'm not going to do, this could be very computational, but I'm just going to sketch sort of the computations you would have to do.
May I ask a very trivial question?
Mhm.
So in this case, so if P is the 0 ideal, right? 0 ideal is prime in,
Right.
in the integral domain. So F0 is not 0, right?
Well, so yeah, if you put f in the localization at 0,
Uh-huh.
right, that's like embedding f in the fraction field.
Uh-huh.
And it wasn't 0 to start with, so it's not going to be 0 in the fraction field.
Yeah, okay. All right.
But you could run this argument, right? Like, the only way I could get AF equals 0 is if A is 0. But when you localize it at prime, you're localizing at the complement of the ideal, right? So 0 can never be a choice element if it's not in P.
Right. So, so what does it mean to be localizing at 0? It means basically
everything
looking
but
at the
0.
fraction field. Yes. Of
Yeah.
course. Okay, sorry. Okay.
Okay.
Yeah, I knew that it was obvious. It's just that, okay, you know, it's like something that you just have to like sort of
Mm-hmm.
play around with, and you get it. Okay.
Okay. So I can't give you an integral domain, of course. We're going to have to look at something that's a little different. So let A be this ring. Okay. So geometrically, what is this thing? I should say, what is spec of this thing? So we're looking at the prime ideals of this ring, which are the same as prime ideals of the polynomial ring that contain this ideal. So correspond to P in, say, spec kxy with P containing this. But I can actually write this ideal as the product of two other ideals. It's the ideal generated by y times the ideal generated by xy. And prime ideals have this nice property that if it contains a product, it contains one of the two ideals in the product. So P either contains xy or it contains y. Well, this ideal corresponds to the origin in the affine plane, and it's maximal, so you only get the origin from this case. This one, well, you pick up anything, the ideal generated by y is corresponding to all the points lying on the x-axis. So you're going to pick up everything on the x-axis, which includes, by the way, the origin. So we get this twice. So P equals x minus cy for some c and k. Or it's the ideal generated by y. So what we've got then is inside this plane, I've got just the x-axis, but I seem to have the origin twice. Okay. So this would be like the scheme theoretic picture of what's going on. In particular, this is an irreducible scheme, because I only have one unique minimal prime ideal. And it's also sort of clear from the picture that if this is the generic point for the x-axis, its closure is going to capture the whole scheme. Okay, but it's not reduced. Since, for instance, I've got a nilpotent, y squared equals 0, but y is not. Okay. So what we want to do is, the claim is, for all elements of this ring, we're going to get one of three possibilities for the support. It could be empty. I can get the origin, which sort of picks up on this doubling behavior. Or I'm going to get the whole scheme. Okay. So this boils down to sort of a computation. Some of the details of which we're just going to sweep under the carpet.
Did you say before, when you answered me, that there was a unique minimum point for each host? There's
A unique generic point for each irreducible set, yes. Yep. Okay. So, right. So first show that every element of A is uniquely of the form polynomial plus multiple of y. The uniqueness is the only hard part. You can get things of this form just by noticing that y squared is 0 and xy is 0. Okay, so if you believe this, so we set let alpha look like this, and beta look like some g of x plus by. And you just compute alpha times beta and ask when that's 0, because that's going to give you sort of the idea of in which localizations am I going to get a 0 element when I take alpha and put it in the localization. So investigate. So you basically are just investigating the failure of your ring to be an integral domain if you're trying to figure out where the supports are. When alpha beta equals 0, to find possibilities. For sub alpha. Okay, so you can do computations. Things happen. Some natural cases suggest themselves. You pursue those cases and so on and so on. But the summary of the results is this. Okay. So it turns out that the three cases I've got there correspond to the following forms of f. So one, if alpha equals 0, sup alpha is empty. That's the only way you're going to get empty support. Okay. If alpha turns out to be a multiple of y, where the multiple is not 0, then you get the origin. It basically works out that way because the only thing that's going to annihilate alpha is a multiple of x. So if you localize at anything but this, I can find x and I can annihilate my element. But x lives in here, so I can't choose that one when I'm localizing at this ideal. So it does not become 0 in that stock. That's the rough summary of what goes on. And 3, well, otherwise, sup alpha is the whole spec. For various reasons. There are actually like two subcases here. Could be that alpha is just annihilated by multiples of y, but those live in all the ideals, so I can't annihilate them. Or alpha is not annihilated by anything but 0, and so we still can't annihilate it in any of these stocks. So again, if you're intrigued by this, you can do this computation and figure out actually how this answer is obtained. But what is more interesting, I think, is the point I'm about to make. Okay. So you notice, I guess I should draw this other conclusion. So the associated points of A well, the origin is the generic point for the origin. And the ideal generated by y, because the closure of that is spec A. Okay. So you'll notice there's sort of two breeds of these associated points. There are ones that are generic points for honest-to-goodness irreducible components of your scheme, and ones that aren't. So we make that distinction. Okay. I'll say this first. So note, so when you're dealing, of course, with your module equals A, then I can actually get the generic points of all the irreducible components as associated points. We have, if I look at the support of 1, if I look at 1 in any stock, it's never going to be 0. It's always going to be 1. Okay, so the support of 1 is spec A. And so I can break spec A into irreducible components, and the generic points of those are automatically associated points. But there might be others, as we just saw. In this case, A, or spec A, was irreducible. So the only irreducible component of spec A was spec A, so the only generic point that corresponds to that is that ideal generated by y. But we got this extra origin bit here. So those ones we're going to call embedded points. So any other associated points. And it turns out the only time we're going to have these to deal with is in this non-reduced case. If we have a reduced scheme, you're never going to get any of these embedded points. So that's the next proposition. Question?
So just looking at ring, whenever you don't have nilpotence, you can tell that, or whenever you have nilpotence, you have embedded points, right? Is that true?
Yeah, I don't know if the converse holds. I'd have to think. Yeah, I'd have to think a little more. But
like in varieties, when you look at like, can you tell from the ideal that there's going to be some embedded points?
yeah, you might be able to. Once we have the geometric notion of that corresponds to this, or sorry, the algebraic notion that corresponds to this, I think maybe we can be able to tell that. Okay. And this, I actually think, this is my favorite proof of this talk. It's sort of combining algebra and topology in really, really weird ways, and it all comes together. I'm sure Pat's going to love this.
Yeah.
So if A is reduced, then A has no embedded points. So again, it's going to boil down to a computation of the supports of elements. But you're just going to show that in this case, they're always going to be unions of irreducible components of spec A. So this breaks up into 2 steps.
Remind me what reduced means.
Remind you of what?
What reduced?
Reduced means there's no nilpotence in the ring, non-zero nilpotence.
Okay.
Okay. So step 1 is to show that the closure of df gives the support of f. Which actually is going to sort of capture what you would think the support of a function is in analysis. When you define support there, you're looking at the set where it's not 0, and you take its closure. But we know for reduced schemes, functions are determined by their values at points. So this is exactly the situation where df should be interpreted as the set of points where f doesn't vanish. And we closed it, and that gives the support. So this is, in the reduced case, capturing this analytic definition that we all know and love. Okay, but the proof has nothing to do with analysis. It's really fun. Okay. Not to say that analysis isn't fun. Oops. Yeah, apologies to my comrades in analysis. Okay, what am I doing? Okay, first. So first we're going to show that df is contained in the support of f. If I've got this, then I know support is closed, so the closure is also contained in the support. Okay. So let's take an element and check it out. Okay, so if I've got a prime living in df, then I want to look at whether it's in the support. So I just want to look at f in the stalk at P, or in the localization at P. So look at fp. I need this to be non-zero. Well, note fp is 0 if and only if. As usual, I can find an element not in P such that A times F is 0. 0 is in P. So because we're prime, this is equivalent to saying A is in P or F is in P. This is not true, because I just said I needed A not to be in P. And F isn't in P because, well, P's in df. So therefore, FP is not 0. And P lives in the support. So we have our containment. Okay. The other one is more fun. So to show, I'm not sure I've ever used this topological definition of closure outside of like real life topological spaces before. So to show sup f is contained in df closure, we prove, we're going to do it this way. We're going to prove that every point in sup f and every neighborhood of that point intersects df. So we prove that for all P in sup f, and it suffices to do basic open neighborhoods, because I can always find one inside any open. All dA containing f, or containing P, we have dA intersect dF, not empty. Okay, and the way this is done is like the perfect algebra argument. So we haven't used reducedness yet, and this is exactly where this is going to happen. So I've got P's in the support of F. So I know, say BF is never 0 if B is not in P. Because that's just saying that F is not 0 in the stock, or in the localization at P. Okay. In particular, this is true of A, since P is in dA. AF is not 0. Since P is in dA, which is the same as asking for A not to be in P. Okay. I have a non-zero element, ergo it is not nilpotent, because we're in a reduced ring. So note AF is not nilpotent. So it's not in the nil radical. It is not in the intersection of all prime ideals of my ring. Thus, D of AF is not empty. And what is this? The intersection of dA and dF. There we go. Sneaky. Very sneaky. Okay, but that's only step one. So I've only shown that I can rewrite the support of F as this other thing. Now I need to show that this other thing is always a union of irreducible components of spec A. If I can do that, then I've proved my proposition. Okay. Step two. So we show the closure of dF is just the union of these C's, where C is an irreducible component of spec A, such that C actually meets dF. If I can do this, then I know that all the supports of all my elements are unions of these things. And all of these are irreducible components of spec A. And so the only generic points I'm going to get are the ones that come from those irreducible components. So it'll be done if I can show this. Okay. So for the one containment, first, note again, dF is certainly contained in the union of these C's that meet dF. Because my entire space is a union of such components, and the only relevant ones are going to be the ones that contain dF, or meet dF in some way. Okay, this is closed because of two things. Each C is closed. Every irreducible component just is. And furthermore, there's a finite union. Union is finite. And that's the Noetherian hypothesis coming in. Every closed subset is a finite union of, there are only going to be finitely many irreducible components of spec A in particular because we have a Noetherian scheme. Okay. So therefore, the closure is contained because it was closed. All right, now the other one.
For the other one, you just have to pick one.
Yeah, show each one is contained in the closure, yeah. But this is also a really cool topology. Okay, other way. So if I've got a component that intersects dF, then C is irreducible. So this is an open subset of C, and it's not empty, and it's dense. It's dense in C. All right. Now, C intersect the closure of DF is closed in C and contains our target dense open set. Therefore, it's C. But this is a fancy way of saying C is contained in DF. Closure. And so the whole union is. And we're done. So who would have expected that this weird result about these associated points would have contained all this really, really cool topology algebra mixture? Okay, well, I've got like 2 minutes. It's not worth beginning anything else. Does anybody have any questions, though, about this business?
So I just want to summarize, right? So what happened there is that you basically showed that, what is it? When we're dealing with reduced A, right, you don't expect any weird points to appear, right?
Yeah, if you know the irreducible
these
components,
embedded
you've got
points
them all.
are sort of bad, and we're saying that if as A is reduced, there's no bad points.
Yeah.
Okay? And the only sort of associated points are the points that you expect.
Right.
So, okay.
Very good. So yeah, what's a preview of coming attractions maybe is, so once we have this stuff, there's going to be two important things. If you know the behavior at associated points, you're going to be able to transfer that behavior to your entire scheme. So the first one is if you know, it's what I said about reduced points. So the set of points at which the localization is non-reduced is going to be the closure of the set of associated points that have non-reduced stock. So you just have to figure out which associated points have non-reduced stock and then take their closure. This is incidentally going to provide a proof that the set of reduced, or points with reduced stocks is open, because the non-reduced ones is a closed set, a closure of some set of points. On the same type of token, you're going to show that if you want to know the support of an element of your module, all you have to do is figure out the associated points at which you have a non-zero germ, close it, done. So all you have to do is compute things at associated points. If you have that list, then what seems to be an infinite computation is reduced to a finite number of associated points. Okay, so future speakers will talk about this.
So when you say any other associated point, you mean, do you include any other modular, or it must be the modular?
For the fixed module.
For the fixed module.
Yeah.
Okay, I see.
Well, for the fixed ring in this case. Like you fix A and then just ask
Fixed
about.
n equal to A. Okay, I see.
Yeah. Yeah, this definition only makes sense for the case M equals A. Okay? Well, that's everything.